Okay, Mr. Benson here, continuing on with the 2010 questions. So this is 12 through to 20. Okay, so first question. In a game of tennis, a ball is thrown vertically upwards. At the top of its motion, it's momentarily stationary. At this point, it is hit forward horizontally by the racket. And in a particular serve, the ball of mass 57 grams is given a horizontal impulse of 1.7 kilogram meters per second. First thing I'm going to think about here is that my mass is 0.057 kilograms. You won't get anything right if you don't convert that. Okay, so what else can we think about? Basically, effectively the ball is completely still at the moment that it's hit, so we don't need to worry about any sort of initial velocities or anything like that. Okay, so the ball is in contact for a period of 0.008 seconds, and we're trying to find the average force. Now, if we're interested in force and time, then we're interested in impulse. Now, we've already been told what the impulse is, I equals Ft, so the force is going to be the impulse divided by the time, so it's going to be 1.7 kilogram meters per second divided by 0.0080 seconds, which is going to be a reasonably high amount of force. And we get 212.5. Now we've got two significant figures. I'm going to say 210 newtons. If I'm doing calculations with this value later, I am going to use more significance than that, but that's the answer to two significant figures. Now that's it for that question. Okay, so moving on. So we've got a spring question. So we've got to think about strains, spring constant, strain potential energy, that kind of thing. So an ideal string with a 2 kilo mass attached. It's held so the spring is not extended. So our extension here is 0. Down here our extension is 0.4 meters. So we've got 2 kilos of mass. Now what that means is the weight force, which is extending the spring, or the force which is extending the spring, is the weight, which is mg, 2 times 10, which is 20 newtons. Now we know that x is 0.4 meters. The force on a spring is minus kx. Now I'm going to ignore the minus sign on the k at this stage because it's not important. So all we need to do is substitute in our values here. K 0.4. So k is going to be 20 over 0.4, which is 50 newtons per meter. Okay, the next question is asking us to think about the difference in the magnitude of the total energy of the spring mass system between 5A and 5B. Write your answer in the box and show you're working in the space provided. Now, when I first thought about this question, I thought about it incorrectly, because you are thinking, or you may think that energy is conserved, which is sensible, and in a lot of the kinds of questions we've been looking at, that's the right assumption. But there's a problem with this question. If you think about what's happened in these two examples, now at the starting position, we've got no extension, we've got the maximum gravitational potential energy, and we've got no strain potential energy. At the lowered point here, we've got no gravitational potential energy, relatively speaking. We've got our maximum strain potential energy, but it's wrong to assume, as I did the first time, that all that gravitational potential energy has turned into strain potential energy, because if you were just to, in order for the energy to be conserved, you just have to drop the spring. Or drop the weight rather, and it would bounce on the spring, and there would be kinetic energy present as well. But in this case, there's no kinetic energy present. So what's happened is that work has been done on the system as the hand is lowering the weight, which has removed some of that kinetic energy, and it has, the other way of saying it is that the weight has done work on the hand, and some of that gravitational potential energy has been transformed into the work done on the hand. That probably makes more sense. And so you have less energy in total at the bottom than you did at the top. Now, this is easy to see if we just do some calculations, which is what they're asking us to do. So if you assume, even if you assume that it is 0, as soon as you start to do a calculation, you're going to realize that you've got the wrong answer and things don't quite make sense. So gravitational potential energy is mgh, which is 2 times 10 times 0.4, which is 8 joules. Now, the strain potential energy is a half kx squared, which is a half times 50 times, now the extension is 0.4 meters squared, and that is 4 joules. So the difference, the gravitational potential energy minus the strain potential energy, 8 minus 4 equals 4 joules. So as soon as you do some calculations on this one, you're going to see that there's a problem. It's not that the energy is conserved between these two situations, and there is a difference of 4 joules. Okay, so we've got physics students are conducting a collision between two trolleys, so we've got masses there, they have different masses. One of them has a spring between it, which gets compressed by a certain amount. We're told something interesting here. The collision is elastic, and there are no frictional forces, which is pretty common. Let's move on and see what other information we might have about this question. So we're given some graphs, and we're going to be asked to think about those. So which graph best shows how the total kinetic energy of the system varies with time before, during, and after the collision? Now, we need to think back here about what we're told. It's an elastic collision, which means the kinetic energy is the same before and after. So that probably narrows down the graphs we can look at. Well, there are A, B, and D all have kinetic energy that is constant before and after. But the important thing is to think about what's happening during the collision. Now, during the collision, which is between sort of L1 and L2, so in this phase here, the spring is being compressed, which means that some energy is being converted to strain potential energy. Now, that means that our kinetic energy must be less because the total energy is always the same. So the only graph which can be right is A. So EK1 equals EK2, they're conserved, but in the collision, there is strain energy, so EK decreases. Moving on, which shows the total momentum of the system varies with time before, during, and after the collision? Explain your answer. Now, this is something of a trick question because momentum is always conserved. So we don't need to think about this one overly. The only answer that suits is B. Momentum is always conserved. Now, our last question, if the collision had been inelastic, which graph would best show the magnitude of the total momentum of the system before momentum varies with time, magnitude of total momentum varying with time before, during, and after the collision. Explain your answer. Now, oddly enough, that is exactly the same as our previous one. It is B because momentum is always conserved, so same answer as in the previous question. I think what they're trying to do here to a degree as well is to perhaps throw you a little bit with what they're asking about, because you're actually reading this, if the collision had been inelastic, well, if it was inelastic, the kinetic energy would be different before or after. And so you might go, okay, well, they must be talking about graph C. But the question is still continuing to talk about total momentum, which is always conserved. So again, B is the answer. Okay, last couple of questions. The International Space Station is currently under construction. We've got some information about it. The following data may be needed, doesn't mean that it is. What is the weight of the ISS in orbit? Now, weight is the force of gravity. So this is F equals Gm1m2 over r squared. Now, all we need to do is substitute in here 6.67 times 10 to the negative 11. Sorry for my terrible writing. The mass of the Earth, 5.98 times 10 to the 24 kilos. The mass of the space station is, where's that gone? 3.04 times 10 to the 5. And this is divided by the radius of the orbit squared. So this is the radius here from the center of the Earth, 6.72 times 10 to the 6. And that is squared. So you can plug all that into your calculator in one go if you're careful. .04 times 10 to the 5 divided by 6.72 times 10 to the power of 6 all squared, and I get so this is a reasonably big number. Two, 6, 8, 5. Now, sorry, I'm about to mess this up and have far too many decimal places on this one. 6 point, I should have about 3 significant figures on this, so 289. I'll write that again. So 289,000 newtons. Now this seems like quite a lot, because we're thinking about something orbiting in space. It's not actually orbiting a huge distance from the Earth. And it is a reasonably large object. So, let's move on with that one. Radius of the Earth. Yeah, you can see in fact that the if you think about the difference between the radius of the Earth and the radius of the orbit, compared to the Earth, it's actually not much at all. So the difference in the gravitational field at that point is actually quite small. It's orbiting relatively closely to Earth. Okay, moving on. What is the period of the orbit of the ISS around the Earth? Now, if you think back to what we just looked at before, it's pretty close to Earth. It's going to be moving relatively quickly. The orbit should actually be a pretty small number, so we just need to put in some information about this. Now, this is one of these equations where our best option is to use r cubed over the period squared equals gm over 4 pi squared. So r is going to be the cube root of gm period squared over 4 pi squared. Now, what we're talking about here is the mass of the Earth, which is 5.98 times 10 to the 24. Now, I've done this completely wrong, haven't I? Because we're trying to find the period, excuse me. So, in fact, I've got to rearrange this again. The period is going to be the square root of 4 pi squared r cubed over gm. So I'm just going to sub all this in, 4 pi squared. So the radius, in fact, we already knew, that is the 6.72 times 10 to the 6. and so that is all cubed, and 6.67 times 10 to the negative 11 times the mass of the Earth, and we've just got to carefully sub that in and see what we get. So the square root of 4 times pi squared times 6.72 times 10 to the 6 cubed divided by 6.67 times 10 to the negative 11, the mass of the Earth, which is 5.8 times 10 to the 24. Okay, so what I end up with is 5,480 seconds. Now there's 3,600 seconds in an hour, so this tells you that this is orbiting the Earth once every 1.5 hours, so it is travelling rather fast. Okay, moving on. Now, when the ISS is completed in 2011, its mass will have increased. Will the period of the orbit around the Earth be greater, the same, or less? It will be the same. Now, the question doesn't ask for an explanation, but if you look at this equation, there's only one mass that's relevant, which is the mass of the Earth. The mass of the satellite is unimportant. The period will be the same.